All right, let's take a look at this problem and calculate what the forces at C would be in the moment. And then actually I'm going to step you through how to find the shear moment diagram for this particular problem. Okay? So the problem's done. So I'm gonna kind of go right through everything. So let's look at the free body diagram right now. So we have AY, we have F, which is a function of that distributed load. We have BY, which is at that bearing. And then we have 225, which is not at the end, but inwards a little bit on the shaft. Okay. Now, how do we find F? Well, this is basically a uniform one. So you take 800 and you multiply by that distance, which is 0.15 meters. So that's 120 newtons, and it acts right at the center of that section of that shaft. Okay. Now, what we need to do is, in order to find AY and BY, you can either take the moment at A, solve for BY, or take the moment at B and solve for AY. What I did is I took the sum of the moments at B, set them equal to 0. So you get AY times 0.4, and I'm assuming clockwise is positive direction. And then I'm subtracting F, which is 120, times the distance away from B, which is 0.075 plus 0.05 meters. And then I am adding 225 times 0.1 because that's the positive force moment. Okay? So again, take the moment at B, make sure you pick your right directions, find your perpendicular distances, and multiply them by your forces. So AY becomes negative 18.75, so technically it's downward. Okay. Now if I sum the forces in the Y, I can then use that to find BY. Okay, so we know AY now, we know F, we have 225, we can solve for BY. Again, I picked upward as my positive direction, which I can write that down. Upward is positive. Okay. Then we have those. What we can do is we can basically do a free body diagram at C. So we got AY, F2, and then we have the moment, we have NC, and we have VC. Okay. So if you scroll down here, F2 now is 800 times 0.05 meters. Okay. Because we're only looking at, if you notice, C is only 50 millimeters. So you have to convert 800 times basically your 50 millimeters to get that force, which acts at the center of that section, okay, which is 0.25 meters, or 0.025 meters, sorry. Okay, so 800 times 0.05, 40 newtons. So 40 newtons now is acting on that shaft at the center. Okay, now basically what we have, let me zoom out a little, right there. If we sum the forces in the X, the Y, and the moment at C, we can find what we need. So when we sum the forces in the X, positive is to the right, NC is 0. When we sum the forces up, we get negative AY minus F2 minus VC equals 0. Okay, so we get negative 18.75. We get minus 40 newtons minus VC. So you get negative 58.75. Okay, if you notice, I did make AY going downward now, okay, which is flipped from what we had, just to make sure you're clear on that. All right, now the moment at C, we have the moment at C, which is MC minus F2 times 0.025. Again, positive is counterclockwise now. Okay, we know our distance, we know our force, which is 40. We can now find that. Minus AY times 0.25, because that's the perpendicular distance. And this is a negative moment. Why? because it's going this way around. Same with this. Okay, and we picked this way as positive. So when we do the moment, we get 5.69 Newton meter. Okay, so that's just that. Now what I'm going to do is I'm going to show you how to calculate this, which is your shear and moment diagram. Okay, so shear is at the top as a function of x, and then moment down below. Now if you notice, I believe the maximum moment is negative 22.5, if I recall. So you can use that moment in the equations that we talked about before with bending, with sigma max is m over the section modulus, s, and you can figure out what your stress is, the maximum stress. Then you can go back in the tables and say, we can use steel because it's less than or greater than that stress. Okay, so you're kind of you can almost design that shaft. All right, let's take a look at how we do a shear moment diagram for this particular problem. Okay, so what we need to do is we pretty much need to look at the sections where the diameters are different, as well as where forces are being acted on. Okay, so we're going to have 4 sections, x1, 2, 3, and 4. And we're going to first look at between 0, which is right here, to point 2, which is, sorry, I wanted to erase the blue there, to right here. Okay, and we're looking at that section. Okay, however, we're going to kind of look at it like from here, and we're going to look at what the shear in the moment is. Okay, we're going to look at it here, we're going to look at it here, and all the way to point 2. Okay, does that make sense? All right, so if over here in my sketch, I don't like to do it right at point 2, a little bit before, like this would be point 2. Okay. But we're going to basically look at the shear and moment from 0 to point 2. So anywhere where I have those dotted slices. So the way we do this is you draw this sketch out, and you label x1, and then you label the forces that are being applied. Okay, so here we only have AY, but we have the shear force we have the shear force V, and then the moment M along from 0 to point 2. Okay, so what we do is we sum the forces in the y, set it equal to 0, up is positive, so we have AY minus V equals 0. And then we said, okay, V is equal to AY, so it's negative 18.75 newtons. Cool. Then we take the moment, set that to 0. Then we have the moment at that spot. And then we're assuming counterclockwise is positive, so we say negative AY times x1. Okay, because that is our distance. So the moment along from 0 to point 2 is negative 18.75 times x1. Okay. So again, look at the section you're looking at, draw your free body diagram, label your x, sum the forces, sum the moments. Okay. And then over here, basically we have the shear and moment diagram like a sketch I did before I did it on the computer. So if I zoom out a little, from 0 to point 2, which are these 2 lines here, okay, the shear is negative 18.75, and then the moment is linear line down to right here, okay, which is, I believe, negative 3.75, because x is in meters. Okay, all right, now let's look at, let's see, where are we? Right here. I'll zoom right in. Let's look at 0.2 to 3.5. Okay, so 0.2 to 0.35. Okay, so that is the location from like this location right here. Okay, so we're kind of looking now at that section where the weighted distribution is. All right, so again, let's zoom right in here. Go right there. We draw our sketch. All right, we label our x2, which is this distance here from AY. Label AY. Here is our force, okay, from that weighted distribution, and it acts a distance d from this point over to the center of that. So here is it's 800 times x2 minus 0.2, because this distance from here to here, that was 0.2. So that gives us this distance right here, right? So if this is a weighted distribution of that, right, it would be 800 times that distance, which is this, okay? So the distance from here to here we can call x, which is x2 minus 0.2. All right, I did it in terms of x2 because that's what our distance is going to be, okay? Because x2 is this total distance. So the forces we have in this section are AY and this F, and then the shear in the moment along this area, surface area, okay? So if we sum the forces in the Y, we get AY minus F minus V, 18.75, okay, because it's negative because of our calculation, minus 800 times x2 minus 0.2 minus v. And then we rearrange and solve for our shear force at that location. Okay. So this is going to be the shear force from 0.2 to 0.35. Okay. And then, in order to find the moments, we take the moment, set it to 0. Okay, let me keep it right there. So the moment minus AYX2, because again, that's a negative moment, plus F times the distance. Okay, so if we are, I already told you, let me do this in light blue, that this distance right here was X. X was x2 minus 0.2, right? Because we defined x2 to be the whole length. We divide that by 2, that's our distance here, because this is where the force acts, okay, is half of that distance. So that would be D, and then we can plug in what F was, and we can finally manipulate what the moment will be, and it's a quadratic, or it's squared, okay? Minus 400 x2 squared plus 141.25 x2 minus 16. So that's the shear force in the moment. Okay. Now, if you want to do some calculus, if you take the derivative of the moment with respect to x2, you get negative 800 x2 plus 141.25. That is your shear force. Okay. You could also integrate V to find your moment if you wanted to do that, okay, by applying your initial boundary conditions. But we're just going to do it this way. I just wanted to show you that you can take the derivative, use calculus. So if we go back to this was my hand sketch as I was doing it. This curve, this is a curve to the second order, right? And then here, though, is linear, okay? All right, let's keep going. So the next section we need to look at is, if you notice up here, is we have a force By here, okay? So we need to have something now between these two sections. So 0.35 to 0.4, which it would almost be it would eventually be to B, okay? So we have AY now. We have F. We have now V in the moment. We defined X3 from AY over. Okay, pretty much right to there. This now is what we did way before, and it acts 0.275 from AY. Okay. So we have AY, F, shear in the moment now. Okay. And again, this will go from that section from here to B where that force is. So we have AY minus F minus V. And then we have V equals negative 138.75. So that's a constant in this section. Then we sum the moments. Zoom out a little. Moment minus AY times X3 plus F times X3 minus 0.275, because, I'll do it here, this distance is what we're looking for. Okay, how far, what's the perpendicular distance away from where we're calculating the moment. Okay, then we go ahead and plug everything in. All right, and we end up getting the moment to be linear relationship. Okay, and again, if you take the derivative, you get 138.75. Okay, and then the last one is 0.4 to 0.5 because you have that other force here. So this is at B, and then this is where that eventually will, like this last dotted line is where that last, what is it, 225? Yep, X. So we have to do that section. So 0.4 to 0.5, we defined X4. We have AYF, and we also have BY now. And again, we're looking pretty much at section B to that last force. Okay. So we look at all the forces, AY minus F plus BY minus V. Okay. We got negative 18.75 minus 120 plus 364. And we get 225 for the shear. And then we have the moment minus AY times X4 plus F times X4 minus 0.275. But again, this is that distance we're looking for. Minus BY times X4 minus 0.4, because this again is the distance from here to here we're looking for. And we can get the moment in this section to be 225 X4 minus 112.5. Okay, so then we can go ahead and look and plot the shear and moment diagram for each section. Okay, and then you could find the max moment, negative 22.5, I believe it is. And if you wanted to, you could use that in your flexure formula to figure out your stress. And if you wanted to size this, you could use that formula. Okay. So again, shear and moment diagrams, you got to look at each section where the diameters change, where there's forces, and you have to split them up like that. Okay. Hope this helps, and have fun.